Okay, so we did some examples of computing directional derivatives. I want to do a little bit more with that today. And then do the beginning of the next section. So, interesting example. So this example is going to come up again in a week or a little bit more. But basically, since I use the same example every class, I have a pet anteater that I keep lying around who lives at the origin. So here's my purple anteater. Not looking very interesting. Okay, so here's a purple anteater. What's the purple people eater? Well, you can be a person if you prefer. I was just going to put an ant somewhere. So here's an ant. So if Nick wants to volunteer, he can be a people there, and I can be a purple people eater. So the question the ant wants to ask is, He's a sophisticated ant. He sees the purple anteater and he does not like what he sees. So he wants to figure out what direction he should go to get away from the anteater as quickly as possible.
The opposite direction. The opposite.
So, all right, let's put this into math.
The negative direction.
What function is the ant concerned about? Distance from the origin, which is where the purple anteater is. So the ant considers thoughtfully the function distance from the origin. And the ant wants to know if he's at a position A, for ant, of course, what direction should he move to get away from the anteater as fast as possible? So, given a point A, given that the ant is not at the origin, what we're interested in is, what can we say about the directional derivative of f at the point the ant's at in the direction of some vector v? So this is in the same spirit of that Weber problem we were just talking about, where you're trying to figure out a vector v that gives you biggest directional derivative. So what does your instinct tell you, since you've spent lots of time being an ant trying to escape an anteater?
Just go A. Just go in the direction of A.
Go in the direction of A. So presumably, going towards the origin would be a stupid thing to do, but going away from the origin, directly in the radial direction, in the direction of A, would be an intelligent thing to do. Can you all reason that to yourselves?
Yes.
Allison, you agree? Okay, so what if we take a unit vector in the direction of A? Can we actually compute this directional derivative? I only have so many favorite examples. So what's the definition? Well, let's go back to our limit definition to make sure you learn it. What do I do? F of A plus TV minus f of A over T, which we also said was the derivative of moving along this line, right? Taking the function along that line. So we could take the derivative at time equals 0 of the function where you plug in the parameterization of the line, so that would be A plus TB. Same thing, it really doesn't much matter. So what is f of A plus TB? Or what is the composition with this? Well, we just take f, right?
A plus TB, yeah.
So f of A plus TB is magnitude of A plus TB. Subtract magnitude of A over T. Now this looks scary, and I don't want you writing out formulas with square roots of sums of squares, and I don't want that at all. But if I'm moving in this direction, we've got magnitude of A plus T unit vector in direction of A. So this looks like a bunch of alphabet soup, but it's really not that bad. So what is this?
So that's just A plus square root of 1 and stuff.
If you take A plus T times a unit vector in the direction of A, what length vector do you have?
A plus 1.
T plus 1. T plus 1.
A plus 2.
Right? You've taken A and you've moved T units further in the same direction. So how far are you from the origin?
A plus T.
Distance of A plus an extra T units. But you can work that all out from the math here. You can factor out the vector A, pull its magnitude out, and then you would have 1 plus T over the magnitude of A, and so this is what you get when you simplify that. So you can check it algebraically. What do I get?
1.
1. Does this come as a shock to anybody?
No.
No. For every step you take walking along that line, you increase your distance by 1 step's worth. So the rate of change of distance is 1. And if you went in the negative direction, what would the directional derivative be? Negative 1.
Because you'd have minus T. A minus 1.
What do you think happens if you decide, if the ant might not be the brightest ant in the world, and he decides to walk in this direction? What do you think the answer is going to be?
0.
Why?
It's in between 1
It's
Because like
perfect.
if you took a minute step, we the radial direction, so you always circle around. Yeah, it's like.
So instantaneously, good. Sammy's saying, if you imagine walking instantaneously in that direction, it's as if you were moving on a
circle.
centered at the anteater. And if the ant walks on this circle,
Its distance is a
how's his distance changing? It's not.
But he might confuse the anteater. The anteater might get dizzy if he goes in circles.
Yeah, it's a
So,
possibility.
moreover,
Psychology.
we note
To a question. Fast ant, really slow ant.
that the directional derivative is 0 when the direction vector is orthogonal to A. Because instantaneously, the ant is walking on a circle. Or if you're in higher dimensions, it would be a sphere centered at the anteater. So the distance from the anteater isn't changing. Okay, so that, we're going to come back to this example multitudinous times. We've only been show up in a related rates problem in your web work next week. So keep this example in mind. All right, I promised you, before we do one more example, quick discussion, likewise in the book. But we discussed this the other day. If you change your vector by scalar multiplying it by c, what do you think should happen to your directional derivative?
So this be C direction.
So the c should pull out. So what we were talking about was, on Wednesday, was thinking about directional derivative is telling you how fast f is changing as you move from a with a velocity vector v. And if you scalar multiply, if you scale your velocity up, f changes that much faster. But I just wanted to remind you, so this is sort of a linearity property. The scalar pulls out, like it does for linear maps. That's going to be important soon. But let's just check. Let's just verify this from the definition. So what is the directional derivative in the direction of CV? It's the limit. Yes, I am going to make you know this definition of what?
A plus TC.
F of a plus t times the vector CV minus f of a all over t. Now you, way back at the beginning of calculus, you had to do limits like this. Where they would stick, you knew something like the limit of sine theta over theta as theta goes to 0, and some mean teacher would ask you what the limit of sine 5 theta over theta was. Tim's smiling. You remember doing stuff like that? Before you ever saw L'Hopital's rule or anything like that? What was the idea? The idea was to make it look like the limit we know. So this is CT or TC, so I can think of this as combining the scalars. Agreed? And then I say to myself, I sure wish that this denominator was also a CT. Provided C
It's not equal to
is
0.
not equal to 0.
But we kind of
So let's assume C isn't 0 here. Now if C were 0, let's stop and think for a minute. What's the directional derivative in the direction of 0?
there is
Zero.
0.
The function ain't changing very much if you don't get to move. So we're okay with assuming C isn't 0, right? Because in the case where C is 0, this is obvious. Okay, C isn't 0. So as you did in homework, your first or second homework assignment, you think, well, one thing I can do with a constant that's not 0 is divide by it. So I might think to put a C in the denominator. And then I'd have a matching pair of CTs. But what have I got to do if I'm going to put a C in the denominator?
Factor out.
I've got to put one in the numerator to cancel. So I multiply, so this is what I like to call multiplying by a clever 1. There are also adding clever zeros. We'll get to that soon. Do you see that we're done now? How can you rewrite this expression?
Pull 1 out.
Take CT as a variable.
So let's just put a new letter in for CT. Let's let S be CT. C is just a constant, so if T is going to 0, what is S doing?
Going to 0.
Still going to 0, right? Those of you who are in love with deltas and epsilons can modify things appropriately. But if I substitute S for CT, and observe that as t is going to 0, s is going to 0, and vice versa, this is now my definition of the directional derivative, but I have times a c. Done. Okay, so this is useful, and it's important to understand that the directional derivative for us, unlike standard calculus books, where they make you make v be a unit vector, we're allowing v to be any length vector we want. But I did warn you that if you're trying to get the slope of the slice of the surface, you need to make sure your v is a unit vector so that you have rise over run. With the run being a 1, then the rise is in fact the slope. Okay. Let's do one more example before we move on a bit. What do you remember about this function? So if I take the function, it's xy squared over quantity x squared plus y to the 4th away from the origin, and 0 at the origin. What do you recollect about this function?
Not continuous.
Not continuous. But I can still ask you, does it have directional derivatives at the origin?
Probably.
How would you decide what a directional derivative of the origin was? Well, what's the A? 0, and what do I do with V? Since I don't have a concrete numerical V, call it V1, V2. So let's just say dV of f at 0 is the limit. Here we go again. So I'm going to do f at 0 plus TV.
TV.
So x TV is going to be, if you let v be v1, v2, then TV obviously is going to be tv1, tv2. And I'm going to have what? xy squared over x squared plus y to the 4th minus f of 0. And then divide by t, right? I shouldn't have written it that way. I'll switch to the standard way now. So the minus 0 isn't too interesting. What have I got in the numerator?
T cubed.
T cubed, v1, v2 squared. What have I got in the denominator?
2t, or yeah.
Squared
Cubed.
or
There's factor of t cubed.
And I have an extra t from this t, right? Don't forget about that you're dividing by t. So I'm pleased to have that extra t because what do I see? I see t cubed here, t cubed here. So let's factor a t cubed out of both things. And what am I left with?
v1, v2 squared. Or v1 squared. v2 times
T to the who?
t times v2 to the 4th.
T to the what?
1.
2 squared.
Squared. Yeah.
T squared v2 to the 4th?
Yep.
So what happens is I take the limit as t goes to 0. This is,
Goes to 1.
that's 1.
Goes to v squared.
Goes to v1, right?
v2 squared.
Or it goes to 1 of, I don't even know.
It's just V2 squared.
V2
is
squared over
Provided-
V1.
That V1 is not.
V1 isn't 0. If V1 were 0, then I would be moving in the direction of the y-axis, and it would just be a partial derivative, and we already know that if you do that, the function is always 0 on the axes, so we know that directional derivative anyway. But this is sort of interesting. So we know, I think we did this example the other day. If we didn't, you can do it in your head easily enough, that the partials, namely the directional derivatives along the axes, are both 0. So particularly for those of you who have seen calculus before, multivariable before a little bit, this is very important to notice. Here is a function that has partial derivatives, both 0, but other directional derivatives that aren't 0. So if you go in the x direction, it's flat. If you go in the y direction, it's flat. But if you head in some other direction, it's going at some weird slope. So I will no doubt draw you this function again on the computer, and a few others probably on Monday, if I can trust the technology. So this is not continuous, but it has partial derivatives, and it has directional derivatives in every direction. Okay, so we sort of are at the point where we want to say, we had this theorem back in single variable calculus that said, as Taylor told us the other day, a differentiable function is always continuous. So we're sort of wanting such a result now, but we better come up with a definition for differentiable.
Differentiable at every direction.
Well, this guy has directional derivatives in every direction, but he ain't even continuous. So obviously it's a bit more subtle than just saying I can take directional derivatives. So let's go back for a minute to single variable calculus for a minute. If you have a function that's differentiable, I think we may have talked about this the very first day of class when I was giving you a little bit of overview, but I want to make a more specific statement. The derivative gives you the slope of the tangent line at the point. Agreed? Why do you care about the tangent line? Why is it interesting? Best linear approximation, Taylor said. So how would you know that if you looked at all possible lines to this point, that somehow that green one was the best? So in what sense is it best?
It's the way that we get it is by looking at all the lines that go through the 2 points of it, and we take the 2 points and we just make them as close to each other as we can.
Okay.
So intuitively, it becomes the best.
So the limit of secant lines
Right.
is what you're describing. But in what sense is it best? How would you qualitatively say what best means?
Give within a certain error.
Hmm?
It can give within a certain error.
Well,
The range of change at that.
so, I mean, so the word Jonathan's saying is a key word here. He's saying the error. So if you actually examine the error, if you're at a nearby point a plus h, and you actually look at the value of the function, and then you look at the approximate value you're getting from the tangent line, you have an actual error here between the actual value of the function and the value on the tangent line. And that error goes to 0 as I come into the point. Well, but it would do that if I did the red line as well. Right? This error also is shrinking to 0. This error here is also shrinking to 0.
For every point, the error for the tangent line is smaller than all the other errors.
I don't know if I believe that.
No.
I'm not sure I believe
Because
that.
if you drew a point through point a plus h, it would be 0.
What,
If
say
your,
again?
if your point that came through a also went through a plus h, then it's going to be equal to the same.
If you took a secant line.
Yeah.
If you took the secant line through a and a plus h,
Yeah, but
then your error would be
unless the
0.
function is
Yeah.
constant,
Then it's.
that line's going to change as h
Right,
changes.
right, but at that point,
Right.
it's not going to be the least error because you could come up with an equation of a line that has an error of 0 at any given.
So I'm going to call epsilon of h the error here. So let's let epsilon of h, and I'm using a slightly different version of epsilon, but it's not a big deal. Error be f of a plus h, the height of the function, minus the height of the tangent line. That's going to give me the discrepancy. So how do I get the tangent line equation? Well, remember point slope?
Yeah.
So I do y minus f of a over x minus a is slope. So the tangent line is given by y is f of a plus f prime of a times x minus a. Everybody remembers this, right? You take this slope and you shift the line so that up f of a units so that it goes through here. This is like what we were doing with planes back in chapter 1 when we were shifting them off the origin. So what's, if I'm at h, a plus h here, what's the y value? It's f of a plus f prime of a times,
X minus A.
but what's x?
A plus H.
A plus h, so what's this?
H.
H. So that's the error between the tangent line approximation and the actual function. But I'm going to rewrite this slightly in a way that might look more familiar to you. Oops. So this is the error you have using the tangent line. Suppose I put in a line of slope m. We have what for the error? So if I put a little m for the slope on this, just to mark that I'm doing the slope m, I have the same thing, but an m here, right? Oops, I screwed up.
I forgot that.
Bad boy. Minus here, very important. Right, the slope times h is this, and that's what I'm using to approximate the height from here to there, the change in f. Sorry, so that minus is a typo there. So let's look, you guys were trying to talk about how small the error was, so let's compare the size of the error to h. if you've learned about Taylor polynomials, this should remind you of what went on with Taylor polynomials. If you didn't learn this about Taylor polynomials, you should take Math 3100 in the spring, which I will talk about soon. All right, so what do I got when I do this? I get f of a plus h minus f of a minus mh over h. So that's the error relative to the size of your step size or change in x. So this is the relative error in the approximation of the function compared to the change in x. And what does this look like to you? So what choice of m is going to make this relative error smallest as you make h goes to 0?
F prime of A.
That actual thing.
So the optimal m should mean that this limit is as small as possible. And 0 is about as small as I can think of. And that gives you exactly the motivation for wanting the slope to be. The limit of this is h goes to 0, otherwise known as
F prime.
f prime, right? F prime of A. So that's why they didn't tell you this when you took calculus, but this is why the derivative is so important. It's giving you the best linear approximation in the sense that not only does the error go to 0, but it goes to 0 faster than h goes to 0. So the best linear approximation is meaning error goes to 0 faster than h goes to 0. And if you're doing quadratic approximation or cubic and you're doing Taylor polynomials, you're trying to go to 0 faster with your error than h squared or h cubed. Okay? So that's my review of the derivative, and guess what? This is the definition I want to use now in the multivariable setting.
So just multiply it all by x.
So definitions like limit of this as h goes to 0 aren't going to make any sense in multivariable. You can't do it. You can't divide by a vector. So the only hope I have is to look at the error and see that the error goes to 0 faster than I'm approaching the point. And that's going to be the definition. All right, here we go. You've been waiting your whole lives for this on pins and needles to know the definition of differentiable. So, definition, suppose f maps a neighborhood of A in Rn. Doesn't have to be defined on all of Rn, but just near a point A. Maps to Rm, let's say. We say f is differentiable at A if there's a best linear approximation to f. Well, let's see. What do you think a linear approximation should be? I bet it should be a linear map. So this was the propaganda for why we did all this linear map stuff. Because you want to approximate functions that aren't linear by linear ones. So the linear map is going to replace what we had here, that thing. There's a linear map T mapping Rn to Rm so that the limit as the vector h goes to 0 of f of a plus h minus f at a. So this part looks the same, but now these are vectors, and this is a vector input, minus linear map of h. That's the best linear approximation. Should mean that if you take the error, it goes to 0 faster than magnitude h goes to 0. Such a t is called the derivative of f at a written, this is with the notation we use all year, df at a. So this is replacing f prime of a in the single variable case. So what's the picture? Picture's not, I'm not quite so good at drawing this by hand usually. There's a nice picture in the book, but I'm scared to put on the projector to show it. And the idea here is, let's see if I can try to draw some. So suppose you're at this point A, and you're trying to understand the function near A. So here's f of a here, that height, and you're trying to move to a nearby point a plus h. Let's do that in a different color. So I'm looking at how much the function changed. So it went from this height here to this height here. And what I'm imagining here is that there is a linear, best linear approximation to this function. So by that I mean a linear map whose graph is a plane that goes through the point on the graph. Well, that's the same thing we did when we translated so that the line went through the point A, f of a. Right? But we did it in single variable, the tangent line went through the point A, f of a. This plane is going through the point A, f of a as well here. And what we're saying is that if you moved on the plane and went over this point, you would have some change along that plane, and that the error between these two should be small relative to the size of h, and get smaller faster than h does as you move into the origin. So it's a two-dimensional version of the picture we were drawing there, and there's a snazzier picture in the book that I spent an hour doing with Adobe Illustrator. Okay. So our goal is going to be compute derivatives, use them to approximate things, use them to do all sorts of word problems just like you did in calculus. But the theory is a bit more subtle. But the coming attractions are going to be here. With this definition. So I'm going to tell you a bunch of stuff now just to let the bag out of the cat. But we'll get to proving these things beginning of next week. So first of all, in fact, indeed, if f is going to be differentiable at a point, then it is going to be continuous at the point. Okay, so this definition of derivative, it is going to guarantee that. And then you might want to say, well, then why did we bother learning partial derivatives if they weren't going to be useful? They are going to be useful. what do you think, in fact, this linear map from Rn to Rn is going to be if it exists? It's all going to be given by partial derivatives. So if f is differentiable, then the derivative is given by a what by what matrix? Well, it's mapping Rn to Rm, m by n. And this is why I've been making you write everything with column vectors, because otherwise at this point everybody gets hopelessly confused. You're going to take the partials of the ith component of f with respect to the jth variable at A. So f here is going to be the function whose components are f1 to fm. And so what you really want to think about, we'll have, again, there's going to be rows and columns, but you're going to want to think about the rows come from taking the partial derivatives of each component function. And so the x's go across this way.
So, conceptually, like, the function f equals like a vector where f1, x1 equals.
So f of x, all these things are functions of x. But if you had, so let me erase this because it's now illegible. So in particular, what's gonna, if you had a, if m were 1, if you had a scalar function, then df at A, no vector now, is just going to be the matrix that's a 1 by n matrix with the partial derivatives going as the entries across. And then this makes sense because you're going to want to multiply it by a vector with n components. It works out exactly, right? Row vector with n things, column vector with n things. And so the rest of the bag that comes out of the cat is if f is differentiable, do you have a snazzy way to find directional derivatives? Well, so first of all, it shouldn't be so surprising that you got the partial derivatives there, because after all, it should be that if you think about setting h to be t times v, if you were thinking about wanting to know how the function changes as you move in the direction of v, you would plug in that, and you would have f of a plus tv minus f of a minus the derivative applied to tv all over the magnitude of tv, and this should go to 0 as t goes to 0. So I'm just substituting h equal to that and saying, notice what I'm getting here. This looks a lot like taking directional derivative. So this we will show next week that this shows that if f is differentiable, then in fact, what should the directional derivative be?
It should be equal
It's just going to be the derivative
to over.
applied to the vector v. You take your derivative matrix, multiply it by v. So if you know you're differentiable, and this is not how you were supposed to do your web work, because we haven't yet proved any theorems to tell you functions are differentiable yet. So for web work due this weekend, you're supposed to be doing what we did on Wednesday. But once the dust has cleared, and we have some theorems that tell you functions that look nice are in fact differentiable, then you will have the partials, and you will take that and multiply by the vector v, and that will be computing the directional derivative. And that should look familiar to people that have seen this stuff before. Not identical, but it's familiar. So let me just close with a point of logic here. And I should put big red important by this. Suppose you have a function and you compute its directional derivatives, and this rule does not hold. What do you conclude? F cannot be differentiable to A. You remember the example we had on the board with the discontinuous function that had the x squareds and 1/4 in it? And we had this formula. I think that's what it was.
Yeah.
And we had both partials equal to 0. I'm pretty sure that if you put these partials into a matrix, you would get the 0 matrix. And then we're supposed to multiply by the vector v1, v2, and it's supposed to give us this. Not very likely. So what do you conclude?
Not differentiable.
Not differentiable. How did you know that anyway?
It's not continuous.
Not continuous. If it were differentiable, it would have to be continuous. So you have two ways of verifying that in fact it's not differentiable.
Is that two-way? Is that a two-way?
No.
Okay.
All right, so we'll pick up with this stuff on Monday. Then crank them on homework.